Okay, it's normal. Dear conference organizers and esteemed audience, it is a great honor to be part of this event and to present our research today. Before I move on to the main subject, I begin by factorizing the title into independent yet meaningful parts. Confidential computing is a technology that protects data during processing by applications or when accessed by users. Effective data protection strategies must address all stages of the data lifecycle: data at rest, data in transit, and data in use. While encryption is a key defense for securing data at rest and in transit, it offers limited protection when data is in use. During processing, data are decrypted and loaded into memory in a readable form. Also, private keys are exposed to applications. This critical vulnerability is often overlooked, especially by administrators who prioritize convenience over security. Confidential computing utilizes hardware-based trusted execution environments, TEEs, to isolate applications and data, preventing unauthorized access or modification, even by cloud providers, network administrators, privileged software, or even software developers. We have three technologies for deploying confidential computing. These are trusted execution environments, hardware security modules, and homomorphic encryption. The latter is the hardest technology due to heavy mathematical apparatus. Confidential computing relies on hardware-level security features to create and enforce the trusted execution environment, ensuring a high level of protection. Here, data is encrypted before being loaded into this environment. Only authorized code can access and process the data. Encryption keys used to protect the data are generated and managed within the trusted environment, often by the hardware itself, making them inaccessible to cloud providers and other users. Edge cloud computing itself is a paradigm shift towards distributed computing, where the specific advantages of edge and cloud are combined to promote reliable systems requiring real-time data processing and analysis. Objectives of this research was to develop confidential computing approaches focused on protecting hierarchical data within edge cloud network. Edge cloud network suggests splitting and sharing data between the main cloud and the range of networks near the endpoint devices. We propose protecting data in this range of the networks near the in this two-level hierarchy by embedding traditional encryption at rest and in transit, while leaving the remaining security issues such as sensitive data and operations in use in the scope of confidential computing within trusted execution environments. Hierarchical data for each network device are linked and identified through distinct paths between edge and main cloud using individual blockchain. Methods for data and cryptographic key splitting between the edge and the main cloud are based on strong authentication techniques to ensure the shared data confidentiality, integrity, and availability. By distributing the shares and ensuring that these shares can be verified as belonging to a valid key, it prevents a single point of failure and reduces the risk of unauthorized access or misuse. Edge cloud computing architecture is a three-tier network. The very basic level in this hierarchy is the network of devices and sensors. The second layer deploys the edge data centers, which perform the operational management of individual groups of edge devices. Aimed at optimization of operational management, classification of devices prior to inclusion to some group supervised by an individual mini data center is suggested. Grouping is performed according to individual groups' mission and level of intelligence. At this level, data collected from sensors will be analyzed and categorized before sending to the main cloud for further processing. The main cloud server is on the top of the hierarchy and still plays its own role in big data analysis, business logic maintenance, and data warehousing. The segmented architecture of the edge cloud network enables splitting the overall workload while leaving some portion of data at the basic level of the network, closer to the devices. In this sense, edge computing shouldn't be confused with autonomous computations and data processing embedded in edge devices. Edge cloud architecture eliminates the necessity of allocating individual bandwidth for each device on the main cloud. Mission-critical tasks are performed at the edge level following the so-called data minimization principle, according to which the amount of data being sent to the main cloud should be minimized while keeping the whole chain of the data under control. Nowadays, edge computing stands at the intersection of 5G, artificial intelligence, and digital transformation, and is a good platform for maintaining real-time information systems, which impose deadlines for producing control responses. For such systems, provision of proper transactions depends not only on their logical correctness, but also on operability in the required time, like urgent medical diagnosis, nuclear plants management, traffic control, real-time speech and image processing, video surveillance, etc. Traditional cloud technologies do not address timely requirements for data processing. Intuitively defined, data intelligence encompasses the processes, technologies, and strategies used to collect, store, and extract meaningful insights from data, empowering informed decision-making and driving better business outcomes. It involves various techniques like data mining, machine learning, and data visualization. In edge computing, data are collected, processed, and analyzed hierarchically at different layers on the network, according to a predefined role distribution scheme near the source where they are generated. The edge level implements timely intelligent tasks such as data aggregation, classification, and validation, peer-to-peer communication among group devices if needed, visualization, data filtering, distribution, dissemination, and replication, data mapping and reducing, caching, chaining, backup, data and cryptographic key splitting, etc. As for any information system, a major issue in edge computing is data security. With many benefits of edge computing, including higher efficiency and lower latency, data generated and stored locally on devices are relatively easy to access due to their lack of cyber protection. Most IoT devices are manufactured without built-in cybersecurity mechanisms, as including them would significantly increase costs and potentially deter buyers. Edge computing paradigm can benefit from hierarchical data construction and management strategy by applying unsupervised learning for classifying the data being stored and processed on different layers on the entire network. In the simplest implementation, we propose splitting data collected at the edge level as follows: leaving and processing timely data at the edge level, and transferring the historical data, also skills, successful or unsuccessful stories, gained through intelligent actions to the main cloud. Here, both successful and unsuccessful stories will be assimilated by the knowledge base and will contribute to the overall system wisdom. The following should be ensured prior splitting the data into disjoint segments. Data distribution within specific groups of devices is the same, or data distribution changes over time. In cases where data distribution is undefined, or probably density function is unknown, investigation of data distribution scenarios prior to data splitting should be done in order to best regroup the devices with similar behavior, such as identical computations, area similar surveillance, etc. Appropriate machine learning tools such as determination of the best fitting data distribution may be implemented in order to recognize data theoretical distributions. Outliers detection is another important point in the recognition of data distribution. Variance and standard deviation detection will reveal new data points that deviate significantly. Those data points will then be marked and processed accordingly. Data distributions revealed, appropriate intelligence can be successfully applied for data analysis and decision-making. This overall process resides at the edge of the entire network. Cryptographic key management in the entire edge cloud network administers the full life cycle of hierarchical cryptographic keys. Note that edge-level encryption secures the data collected from edge devices, such that no level in computing receives the raw version of the payload directly. For effective and secure key management, hardware security modules, Yeghisabets, and related secure zones at the edge level should be embedded. This will ensure supporting sensitive operations like key generation, key secure storage and key encryption, key distribution, backup, verifiable secret splitting and sharing, etc. It is worthy to note that we do not split original key itself, but share the responsibility of the secret by embedding secure computations over the secret. This will eliminate the brute force attack on the portions of secret keys. We also involve verifiable secret sharing for their combination and algebraic verification. The process of combining the shares undergoes to secure computation within the edge cloud trusted execution environments to algebraically validate the claimed shares. Each time a transaction is activated on the edge cloud network, firstly, a verification of the validity of the key shares is performed. It is strongly recommended to limit the amount of information protected by a given key and the amount of exposure if a single key is compromised. For hierarchical key management, a hybrid approach is suggested, which combines centralized and decentralized strategies. Here, cloud layer may act as a trusted authority, PKI, public infrastructure, or KMS, key management system, to initialize and distribute long-term keys. Edge nodes may use derived session keys or ephemeral keys. Asymmetric cryptography may be used for initial authentication, then symmetric keys may be applied for real-time speedy computations. In case PKI is not available or there is no need for certificates, identity-based encryption or certificate-less PKI may be deployed. Here, keys will be generated based on node identities, making management simpler in highly dynamic environments. Blockchain-based key management will deploy immutable and distributed ledger used to store public keys, verify device credentials, or manage trust. Group key management may be deployed for multicast broadcast scenarios among a set of classified edge nodes. Techniques are logical key hierarchy, one-way function trees, or contributory key agreement, best for collaborative edge clusters. Dynamic key update and revocation is necessary for supporting frequent topology changes. Here, key-insulated cryptography, time-based rekeying, and blockchain-triggered revocation may be deployed. Key-insulated cryptography suggests dividing the key into components and using a helper system to periodically update or refresh the keys. This approach minimizes the damage if one part of key is compromised. Time-based rekeying is a security feature where the encryption keys are automatically regenerated after a specified period of time. This prevents the compromise of long-lived keys by using a timer to initiate the rekeying process. Blockchain-based key revocation offers an enhanced alternative to traditional centralized methods for key and certificate revocation. The amount of available and intelligent data will be consequently decreased and reside in the scope of confidential computing in edge cloud hierarchy. And most of cryptographic operations will be delegated to edge servers, and cryptographic hash functions with these 5 mandatory properties will be involved to ensure data integrity. Cryptographic hash functions should satisfy these 5 strong properties. It should be deterministic, it should be preimage resistant, second preimage resistant, collision-free, and small changes in input data must result in significant changes in the output hash. SHA 256 and higher satisfy these conditions and may be successfully applied. In edge cloud networks, confidential computing is deployed strategically across both layers to safeguard sensitive operations while supporting performance, decentralization, and trust. On the cloud layer, which supports scalable and centralized confidential workloads, cloud trusted execution environments may be deployed to protect data analytics, AI/ML model training on sensitive data, and key management inside the hardware security modules within the TEs. Here we have greater computational power, centralized trust anchors, and strong auditability and access controls. On the edge level, we may deploy lightweight and local trusted execution within edge TEs to protect local preprocessing of sensor data, secure feature extraction, private inference using ML models, and secure communication, encrypting data before cloud upload. It also reduces exposure to physical or network attacks and supports privacy preserving local decisions. Secure communication across edge and cloud implements end-to-end encrypted channels by using TLS 1.3 or QoS between TEs. Remote attestation ensures both edge and cloud enclaves are trusted before exchanging secrets. Data sharing is the process of making the same data accessible to a number of users or applications based on the one-to-many principle of association. Note that data within a device are under the sole control and are of a required physical and cyber security. In this sense, the edge level must ensure the confidentiality and integrity of data being shared or exchanged in order to exclude exposing data to unauthorized access. While splitting is done within a specific edge data point and under the local control, sharing data parts results in transferring them, and this is when solely zero trust-based identification and strong authentication of the shares should be mandatory deployed. The amount of available and intelligible data consequently decreases and resides in the scope of confidential computing. Secure data transmission to cloud may be obtained using a series of protocols, end-to-end encryption, and data tagging with metadata such as timestamp, location, priority, etc. Identity management ensures automatic identification and authentication of edge devices and relevant edge computing resources. For this purpose, the following mechanisms should be embedded at the edge level: IoT device identity lifecycle management, authentication in order to ensure validity of entities within the network hierarchy. This is the first step to perform any computing operation before moving to the next steps. Authorization, it always comes after the authentication and allows operating solely verified entities. Distributed identity management architecture equipped with 5G networks in order to assign unique identities by the software-defined identity management systems. Here, local nodes will share parameters with the local software-defined network servers to acquire identity. Local SDN devices synchronize their identity databases with the main cloud's SDN device. All global SDN devices will also synchronize their databases. Thus, the whole hierarchy in the edge architecture will be strongly identified. Timestamping in an edge cloud hierarchy is crucial for accurately tracking when events occur across different layers of the infrastructure. It involves assigning timestamps to data as it moves from devices at the edge to the cloud, enabling time-based analysis and synchronization across the system. Different layers may generate timestamps, or the edge processor may be responsible for extracting and assigning them. A timestamp is a functional mapping. A is the alphabet, L is the set of literals, G is the global TSA, timestamp authority, the global secure timestamp server data. The TSA will register the current transaction data and time, which when necessary can be verified with the main cloud to resist to replay attacks. S presents the resultant timestamp string. In cases when embedding PKI is expensive, self-certified cryptography may be utilized to implement the registration and at least two-factor authentication of network entities. Meanwhile, authentication is verified each time before edge and main cloud levels interact. Internally generated certificates can be bound to identities and construct the identity and certificate management mechanism based on blockchain. Blockchain identity management systems are commonly used to address security issues such as data insecurity and fraudulent identities. Here, the distributed ledger blockchain will store complete paths, individual or joint, depending on the implementation, for each device having data shared between the edge and main cloud. Labeling of the classified data, their cascading aggregation, validation, classification, and then filtering phases in order to trace the data hierarchical claim and chain from the edge to the main cloud. Edge nodes collect and sign data such as sensor logs, device states, etc. Blockchain logs signed transactions from edge. It stores metadata such as hash of raw data stored in off-chain cloud storage. Cloud acts as a lightweight oracle or analytics engine. It stores large or non-critical data off-chain, such as interplanetary file system, cloud storage, etc. Hash pointers in blockchain enable tamper-proof data integrity while keeping the chain lightweight. Due to resource-constrained nature of the IoT devices, we propose constructing of the edge-to-main cloud blockchain based on secure computations on elliptic curves. Unlike the simplified curves used in traditional data encryption and decryption, the selection of unique points here is done on an original curve in order to meet higher security requirements. Elliptical cryptography is favored in resource-constrained environments due to its ability to provide the required security with smaller key sizes compared to traditional methods like RSA. Initially, prior to regrouping the devices, the ledger is an empty list. The list gets incrementally updated with every new device joining the specific group and presents a dynamic list of unique identifiers obtained in the following steps. For every device in a group, a unique point on the elliptic curve is selected and recorded at the edge secure server zone. AES 256 is applied to encrypt the points according to data anonymization principle. Encrypted data is neither usable nor decrypted, as they are not used in any of further transactions. Utilizing elliptic curves is motivated by an NP completeness of guessing the point coordinates, even if the curve is made public. The encrypted point is hashed with the timestamp. Then second hash is created with the previous content in the public ledger. This step is skipped with the first record. The resultant second hash is the unique ID for a device joining the group. This hash is recorded in the edge ledger. The ledger is transmitted to the main cloud server to a distinct location. Distinct paths for each blockchain provided. Anyway, access control mechanisms that meet the edge computing security, privacy, and data diversity requirements should be upgraded from traditional access control schemes. For this purpose, involving Bloom filter integrated with identity management and lightweight secret key agreement protocols based on self-organized public key may serve as a good basis for innovating edge cloud access controls. A Bloom filter is a space-efficient probabilistic data structure used to test whether an element is a member of a set. Most of existing secret sharing schemes of proven security, like in Shamir's threshold scheme, are based on the assumption that all participating users are legitimate. This approach is prone to sophisticated attacks. The attacker can impersonate a legitimate party without being detected. Schemes of proven security utilize modernization of Shamir's threshold scheme. We propose constructing a verifiable secret sharing scheme based on abstract structures from non-associative algebras. The theory of quasi-groups is a permanently evolving scientific direction. Quasi-groups stand for a generalization of groups without the associative law or identity element. The attractiveness of quasi-groups in construction of verifiable secret splitting and sharing schemes is in their easily programmable nature due to utilization of solely logical operations. A quasi-group T operations satisfy the given conditions. To understanding quasi-groups assumes reviewing, observation how algebraic structures evolve from basic groupoid with a single binary operation to semigroup if this operation is associative, to a monoid if the semigroup has identity element, to a group if every element in the monoid has an inverse, to an abelian group if the operation is also commutative, to a quasi-group if the group commutative, associative, and identity element properties are optional, but division is always possible. It satisfies the quasi-group axioms, which requires that for any two elements there exist unique solutions to equations involving the binary operation. In a sense, an abelian group is a specific type of a quasi-group that satisfies additional conditions: commutativity, associativity, identity, and inverses. Therefore, while a quasi-group might be isotopic to an abelian group, it is not inherently an abelian group itself. Quasi-group with an identity element is called a loop. An associative loop is a group. Ring has two operations: to division ring with 0 denoting additive identity and 1 denoting multiplicated identity was developed, and field is a commutative division ring. Optionally, And optionality of commutativity, associativity, and of the presence of the identity element makes the quasi-group especially attracting in construction of sophisticated secret schemes. The theory of quasi-group is Anders' evolution, unlike most of existing cryptographic construction over the number theory. Quasi-groups are crazy algebraic structures where even mathematicians throw up their hands. To this day, we don't know how many quasi-groups exist for a given order, unless their multiplication tables are Latin squares. Then at least we can count them. The verifiable secret splitting is performed as follows. The order n of the quasi-group denotes the number of its elements, dictates the number of shares. Edge computing paradigm suggests having 2 out of 2 to n shares, satisfying above properties for the secret quasi-group. The 2 shares are encrypted and distributed between the network layers. When combined, the 2 shares are decrypted in the Yeghisabet within the TE, where shares first get authenticated. The proposed scheme eliminates the risk of impersonation attacks against both the edge and the main cloud levels. The shares are verified and at the edge level Yeghisabet by a polynomial time computation. Meanwhile, for the non-legitimate party, this computation will lead to a numerical explosion, guessing the large table of the secret quasi-group. The main cloud site itself is secured by confidential computing. This slide shows the efficiency of involving and for secret chain, we select n-1 random elements from the quasi-group. We compute the shares by using the quasi-group T operations, each resulting in different outcomes, where S's are the secret forms by using the quasi-group T operations, and inverses are corresponding operations ensuring reconstructability. This slide shows the efficiency of quasi-group operations and storage. For a quasi-group of order n, a matrix of size n over n is created. Space complexity is n squared. Computing the parastrophes is a simply square matrix lookup with a type complexity O, big O1. The proposed computational computing scheme involves areas of mathematics under active development. It leverages intractable problems on elliptic curves and a special class of quasi-groups. It suggests edge cloud hierarchy operate under strong authentication, involves verifiable secret sharing, and embeds a lightweight blockchain. To conclude with, confidential computing assumes hardware-level isolation of data processing in a tamper-proof and TEE aimed at preserving data confidentiality, where unauthorized entities cannot view data while it is in use, data integrity, where unauthorized entities cannot add, remove, or alter data while it is in use, code integrity, where unauthorized entities cannot add, remove, or alter code executing within the TEE. Unlike cryptographic keys generated and stored in software, which aren't difficult to guess, maybe, sandboxed enclaves deployed for confidential computing safeguard data in use. Thank you for your listening. Now I'm open to answer questions, if any.